I'm very happy because this is the last colloquium talk of this year, and it's very cold, and I think it's going to be a very memorable day. I'm going to remember this day for a very long time. Okay, so I'd like to talk about enumerative geometry and moduli spaces. So this is one of the areas that I work on, but one of the areas, there are some other areas, but I keep talking about enumerative geometry in colloquium talks because it's easier to explain to general audience. Anyway, but it's a very interesting area, so students must find it very interesting, I hope. So let me explain what's enumerative geometry from starting with a very ancient problem. So the history of enumerative geometry dates back like 22 centuries. Okay, for instance, there is a problem of Apollonius, 22 centuries ago. He asked to construct all possible circles which are tangent to 3 given circles in the plane. Well, let's make it simple. So these 3 planes are just three circles, none of which contains any other, right? So, and what is the answer? So there are 8 circles, right? So 1 circle containing all the 3 circles, and there are 3 circles containing 2 circles inside and 1 circle outside, and there are 3 circles containing 1 circle inside and 2 circles outside, and there is 1 circle which contains none of these 3 circles. Right, so this is an example of enumerative geometry. Okay, and obviously enumerative geometry is just enumeration of geometric objects. In this case, the circles satisfying these the conditions. Okay, so as you can see, enumerative geometry has long history, and everybody knows a little bit about enumerative geometry from junior high school or high school mathematics. But surprisingly, it has very long history, but it's still in the center of mathematics and mathematical physics. Especially recently in string theory, enumerative geometry turns out to be related to gravitation. So it explains gravitation quite surprisingly. So anyway, there is a very high interest about enumerative geometry by physicists. So the question that I want to raise now is, what is a good enumerative geometry? What is a good enumerative problem? Okay. For example, you can think about following problem: how many points are there in the curve xn plus yn plus zn in rational numbers? Everybody knows the answer, right? There's none. Okay, only 200 pages proof. The proof takes only 200 pages. Why is it so?
Take 2 years for 1 page. This problem.
2 years. So why is this problem so famous? I think it's because the answer is so simple. Suppose the answer was like, there is no solution for n equals 5. There are 5 solutions for n equals 7. When n is 27, this number of solutions is 2,864, and that's not good, right? So it's not. Well, nobody will consider it as a good enumerative problem. Okay. So my criterion is very simple. Good enumerative problem must have simple answers. If you have complicated answers, then it's a wrong problem. It's not a good problem. That's my philosophy. So let me give you some examples of enumerative problems. Okay, first question. Suppose you have 2 distinct lines in plane R2. How many points do they intersect? The answer is very, very complicated. Okay, so there are 2 cases. That's already bad. That's bad news. If you have to separate into cases, then it's not a good problem. If 2 lines are not parallel, they meet at 1 point. If they are parallel, then the intersection points gradually if you have two lines and if they become parallel gradually, then the intersection point disappears to infinity. So that's bad news. Okay, what do you have to do? I want to make it simple. I want a simple answer. I want to modify the problem in order to get a simple answer. That's what we do every day, right? Okay, so what we have to do in order to simplify the answer, we have to compactify this. The reason why we get complicated answer is that, well, the intersection point is allowed to disappear to infinity. Let's prevent it, but let's include infinity. That's something called compactification. Okay, so we learned the lesson. We need the compactification. Second question, suppose you have a line in the plane R2, and suppose you have a quadratic curve y equals x squared plus ax squared x plus b. Wow, how many points do they intersect? This problem is also horribly complicated to me. It's very complicated. You need to think about three cases, not just two, three. Okay, when a squared minus 4b is greater than 0, 2 points. 0 when a squared minus 4b is equal to 0, 1 point. But that's okay. You can say that this point is point of multiplicity 2, so you can say it's 2 points. But when a squared minus 4b is less than 0, no points. They don't intersect at all. What do you have to do? Well, there are two solutions actually. One solution is to introduce the notion of orientation, and topologists do that. The topologist's answer is 0. 0 point, 0 point, 0 point. But algebraic geometry's answer is different. What do we have to do? We use complex numbers instead. If you use complex numbers, and if you count the number of intersection points with the multiplicity, then surprisingly, the answer is all the time 2. 2 points, 2 points, 2 points, if you think about complex numbers. So what do? We modify the problem again to get a simple answer. Okay, so here are the lessons we have learned so far. In order to obtain simple answers, in other words, in order to get a good enumerative problem, you need, first of all, you need a compactification. You need to think about compact spaces. Otherwise, you have to divide into several cases, many cases. It's going to be horribly complicated. Okay, and also you have to use complex numbers. Right? If you use real numbers, you have to also think about when discriminant is positive, negative. That's not good. And also, when you are counting, you have to count with multiplicity. Then you can get simple answers. So the lesson is that the ordinary real Euclidean space is not good, right? So you need a complex space. You need to use complex numbers. So a natural setting for enumerative geometry is complex projective space. Okay, let me introduce what that is. So in one sentence, n-dimensional projective space is nothing but the set of lines in n plus 1 dimensional complex vector space passing through 0, the origin. So how do you represent this? So this is well defined as a set, but you want to give a geometric structure, so you need to introduce coordinates for that. Okay, the way we do this is following. So Pn can be thought of as the set of equivalence classes of points in Cn plus 1 minus 0. So the set of n plus 1 tuples of complex numbers, they are not all 0. So it means I exclude the origin. And then you identify two such n plus 1 tuples when one is a scalar multiple of the other. Okay, it means this point and this point represent the same line. Okay. Then obviously n-dimensional projective space is the sum of n-dimensional complex vector space and union of m-dimensional complex vector space and n-1 dimensional projective space. And this space is compact. So Pn is a compactification of Cn. Okay, so first of all, Rn is not good. You have to use complex numbers. So you have to use Cn instead of Rn. And then you have to add something at infinity to make it compact, and something added at infinity is Pn minus 1. Okay, so why do we have this decomposition? Because Cn can be thought of as a subset of Pn, open subset, by this identification. You have n, if you have n complex numbers W1, W2, Wn, then you can associate this point 1, W1, Wn in Pn. This is an n plus 1, 2 probe complex numbers, not all 0. This is an open subset, and the complement of this open subset is 0, Z1, Z2, Zn, but this is always 0, so I can just take this out, delete this, then you get a set of equivalence classes of n tuples of complex numbers, which are not all 0, and that's exactly Pn minus 1. So we call this hyperplane at infinity. Okay, you can do the same thing. Pn minus 1 can be decomposed into the union of Cn minus 1 and Pn minus 2, and you can keep doing this, and so you get the cell decomposition of the n-dimensional projective space. Okay, so everybody knows this and learns this in the first course in algebraic topology or something like that. Okay, so and then what? And what are things that we want to deal with? We want to deal with projective varieties, and what are they? So we want. So let f be a homogeneous polynomial of degree d, positive, and then we make the very simple observation. If you plug in z1, z0, z1, zn to f, and if you got 0, then the same you get 0 if you plug in lambda z0, lambda z1, lambda zn. For any non-zero lambda, okay? So it means that the condition that f being 0 is a good condition even after taking equivalence classes, right? So so that's well. So this is a good condition, even in the projective space after taking equivalence classes. So then we make the definition: a projective variety is nothing but the common zero locus in projective space of finite number of homogeneous polynomials. Well, all of these may have different degrees: d1, d2, dk. Anyway, so my definition of complex algebraic geometry is the study of projective varieties. Okay, and curve is what? Curve is a complex projective variety of dimension 1. Surface is dimension 2, threefold dimension 3, fourfold dimension 4. So real dimensions are 2, 4, 6, 8. You have to multiply 2 for real dimension. Okay, so we thought about some naive enumerative problems, and we found some problems with those ill-posed problems. So now we introduce projective spaces. We introduce notion of projective varieties. Let's see what kind of improvement we got after doing all the work. Okay, so second, well, okay, so let's do enumerative geometry on projective spaces. Question number 3. Let Ci be C1, C2 be curves in projective plane P2. Okay. Now previously we used R2 and we had many problems. So we replace the R2 by CP2, complex projective plane. And then we asked a similar question. So you have C1 of degree 1, C2 of degree 2. C2 of degree D2. So we have two plane curves, degree D1, degree D2. And then we ask the same question. How many points do they intersect? The answer is very clean. This is called Bezout theorem for plane curves. The answer is exactly D1 times D2. It doesn't depend on the choices. I mean, it's true for every pair of curves. You don't have to divide into any special cases. Exactly D1 times D2 for any possible cases. Okay, the precise formulation of the theorem is this: sum of all possible multiplicities at intersection points is exactly D1, D2. So as I said, we have to count with multiplicity. What is multiplicity? Multiplicity of intersection at a point is, well, you can define rigorously or algebraically, but, intuitively, the answer is exactly. You can get a feeling about the notion of multiplicity by this example. Suppose y is equal to x to the k, y is equal to k, then the multiplicity is equal to k. So it's like up to how many terms in the Taylor series you get the same thing. So this is not just Moduli theorem is not just for P2. You can think about the same thing for any projective space Pn, and for that, and you think about n hypersurfaces C1, C2, Cn, and let's say they have degrees d1, d2, dn. Hypersurface is nothing but the projective variety defined by a single equation, and this is dimension n minus 1. If you intersect with the same hypersurface, then the dimension will drop by 1. If you intersect n hypersurfaces, and you get zero-dimensional object, which must be a finite number of points. And the theorem says the intersection points, if you count with multiplicity, is exactly the product of the degrees. It doesn't matter which curves you choose, which hypersurfaces you choose. It's always this number. So I'll give you a proof of this theorem later, just a very simple proof. Anyway, right. So the Moduli theorem is a simple example of intersection theory. What is intersection theory? A very simple definition of this is counting of intersection points of closed subvarieties of a projective variety. So it's a very special case of enumerative geometry. Enumerative geometry counts geometric objects, but this intersection theory is just the counting of points. It's a very special case. Let's just count points. Okay, so in some sense, the Moduli theorem gives us an answer to the intersection theory problems. I mean, counting of points. But how can you count number of how can you count lines, curves, surfaces, many other things, more complicated geometric objects? Okay, so intersection theory is counting of points, but we want to count more general geometric objects later on, from now on. Example, now is a plane, but complex numbers and compactified. How many lines in plane pass through two distinct points? So 1 point, right. So let me give you a proof, because this is something that I can prove in this lecture. This is a proof. A line in plane is given by a linear equation, a0, z0 plus a1, z1 plus a2, z2 equals 0. And if you have two linear equations, they give us the same line if and only if the equations are just related by constant multiples. Okay, so one equation is a constant multiple of the other equation. So, and obviously linear equations are determined by these coefficients a0, a1, a2. So what do? We think about the set of all possible lines in P2, and the set of all possible lines in P2 is exactly the set of three numbers, a0, a1, a2, not all 0. But if you multiply lambda, some constant number, to these three numbers, then you have to identify these two, because they give us the same line. That means exactly the set of lines in P2 is actually P2. The set of lines in P2 is P2. Then we think about the constraints. The constraints are the line should pass through two given points. Let's think about just 1 point. The set of lines in this P2 passing through a given point is what? It should satisfy this equation. So let's say z0, z1, z2, these three numbers are given, then a0, a1, a2 should satisfy this equation. So in this P track, in the space of lines, the condition that the line should pass through a given point gives us a line in P track. So so you have a line, but you have to think about two different points, and the line should pass through to two different points. So it means you are thinking about you're thinking about intersection of two lines in P track. The lines of degree 1, and so by the Moduli theorem, 1 times 1 you get 1, right? So this is a proof, but this is very easy, but it gives you the idea of the whole industry. Okay, second example. Okay, next question. How many conics? A conic means degree 2 curves, right? In plane pass through five given points in the plane. Okay. Everybody knows this answer, right? Even from even junior high school students or elementary school students these days know the answer. The answer is exactly 1, right? Well, okay. Why is it 1? Okay, the answer is very simple. The proof is here. Think about conic, and if a conic is given by a quadratic polynomial in 3 variables, z0, z1, z2, I mean the 3 coordinates of P2. So we can write any quadratic polynomial like this: a0, z0 squared, a1, z1 squared, a2, z2 squared, and so on. So a conic is determined by these 6 numbers: a0, a1, a2, a3, a4, a5. If you know the coefficients, and you know the conic. And like in the previous case, if you multiply some non-zero constant, you get the same conic. So if you think about the space of all conics in P2, then that's exactly P5. You need just know these 6 numbers, and if you multiply a non-zero constant, you get the same points. You have to identify the points. So that's exactly the definition of projective space. So it's P5. Okay, now you think about the constraints. The constraints are the conic should pass through 5 given points. Let's think about just one point, z0, z1, z2. Then these numbers, z0, z0 squared, z1 squared, z2 squared, these are constants now. And a0, a1, a2, a3 are variables now. So the condition that the conics should pass through a given point gives us a hyperplane in Q, in P5. Now you have to think about 5 points, so you have to think about intersection of 5 hyperplanes in P5, right? Each condition gives you a hyperplane, and you want this you want these 5 conditions are satisfied at the same time. That means you're taking the intersection of these subvarieties. So you have to take the intersection of these 5 hyperplanes. By Bezout theorem, you only need to multiply the degrees. But degrees are all 1 because they're linear polynomials with respect to a0, a1, a2, right? So by Bezout theorem, the answer is exactly 1. Okay, this is a proof. Okay, so it's a complicated proof that everybody knew since we were 13 years old. Okay, but as I said, this simple proof contains the most important philosophy for the whole industry of enumerative geometry. What is the lesson? The lesson of these examples is this: if you want to count the number of lines, you have to first think about the space of all possible lines first of all, and then you think about the constraints, and constraints give us subvarieties, and then you have to count the number of intersection points. So you see the difference here? Here on the left-hand side, you have to count lines, you have to count conics, you have to count geometric objects, which may be very complicated. When on the right-hand side, you just count the points. That's the difference. Left-hand side is maybe left-hand side you want to count some complicated geometric objects, but right-hand side you're counting just points. That's the difference. Okay, so if you want to count lines, you think about space of all lines. That's P check. You want to count number of count conics. You think about all possible conics Q. So that left-hand side is enumerative geometry, right side intersection theory. But for that, to do that, you need these spaces P check and Q, the space of all possible lines and all possible conics. So there comes the notion of moduli space. Moduli space is nothing but a set or variety or scheme, it depends on the situation, whose points are in one-to-one correspondence with the collection of all possible geometric objects that you want to parameterize. Okay, so for instance, if you want to parameterize lines, the moduli space is P check. Every point in P check represents a line in P2. If you want to parameterize conics, Q is the moduli space. Every point in Q parameterizes gives us a conic in the plane. So that's the notion of moduli space. Okay, so P check, Q, moduli space. So it's not very complex. There is nothing to worry about. I mean, it's very natural. So modular space, the word looks or sounds scary, but it's not scary. Everybody knew modular spaces since junior high school. Okay, so this is the most important slogan in the industry. Enumerative geometry. Enumerative geometry is nothing but intersection theory on modular spaces. You cannot directly count the number of lines, you cannot directly count lines, conics, surfaces, but that's likely to be horribly complicated. But you convert this problem to the problem of counting points after constructing modular spaces. That's the most important philosophy, and this is the way we solve all possible enumerative problems in algebraic geometry. So that's why modular spaces are important, intersection theory are important. If you want to count curves, then you need a modular space, like Hilbert scheme, Charles scheme, modular stable pairs, and things like that. Okay, so now we gained some insight, we gained some philosophy. Now let's look at some more examples. Question number 6. So we thought about degree 1 case line, degree 2 case conics, and let's say let's just generalize it for higher degree conics. Just P2 is just plain. Think about all possible degree D and genus 0. I mean, so genus is like everybody knows in algebra. How equals is number of. So a complex curve is a Riemann surface, real two-dimensional surface. So you know, everybody knows the classification of Riemann surfaces, right? The number of holes is the genus. Especially, let's think about the genus 0 case. Okay, degree 0, and when degree is equal to 1 or 2, automatically the genus is 0. So it's not, okay, so it's a generalization. So let's count the number of degree D curves of genus 0 that pass through the given 3D minus 1 points. Okay, when D is equal to 1, you have 2 points. When D is equal to 2, you have 5 points. This is a natural generalization of the previous 2 examples, 2 questions, right? More precisely, what we want to calculate is this. So you want to calculate the number of holomorphic maps from P1 to P2, and degree D, and the image of this holomorphic map should pass through 3D minus 1 given points. And we model out some isomorphism classes. Okay, so this is a very simple natural generalization. It could be, I mean, this kind of question can be raised by, well, any junior high school student, right? So, but the answer turned out to be extremely difficult, extremely surprisingly difficult, right? Even degree 1, degree 2 case was very easy, but degree 3 case is also very complicated, degree 4, 5, very horribly complicated. This problem looks very, very classical, very naive, but this problem was solved only recently in 1990s. Only 10 years ago, only 15 years ago, by no one other than Maxim Kusevich. Okay, the answer is this. He gave very nice formula for these numbers. Very. So you learn the lessons here. This problem looks like a very innocent generalization of the previous 2 questions, but it's very, very hard. It's like number theory. I mean, questions that look like naive or simple or innocent are often very, very difficult. Okay? So enumerative geometries problems are often quite difficult like this. Okay, so just one word. So he solved this problem by introducing the Gromov-Witten invariants and localization technique. Okay,
what is process equals 3? Can you count it?
Yes, this formula. So D1 plus D2 are natural numbers smaller than D. So we can just plug in.
So what is the right answer?
I didn't calculate. So. Oh, thank you. Oh, great. Thank you very much. So. I obviously try to run away when as soon as I see the name like conservative. Okay. Anyway, just so we have this formula now. So if you want, you can calculate the numbers. Okay. So next question. Let's think about more enumerative problems. This problem is a very classical problem, and this is one of the examples that everybody learns in first algebraic geometry course. Right? It's one of the beautiful results that you learn in the first course in algebraic geometry. Suppose S is in P3 a surface. So this is a space, three-dimensional space, and S is a zero locus of a homogeneous cubic polynomial. So it's a cubic surface. Now you ask for the number of lines that are contained in this surface, cubic surface. It's just a surface in three-dimensional space given by cubic equation, and you want to find the number of lines contained in this surface. So the beautiful answer is the answer is 29. Okay. So there are several solutions to this problem. So the solution I like is the intersection theory solution. So first of all, you think about all possible lines in P3. Forget about S, just P3. Then that's the set of lines in P3 are parameterized by something called Grassmannian, GR24, two-dimensional vector spaces, subspaces in C4. That's GR24. Then you have a universal family of maps. So universal family of family of two-dimensional subspaces. It is calligraphic U. That's the universal rank 2 bundle, and projectivize it. And then there is a map to P3, obvious map to P3, obvious embedding map, right? And then the answer is this. What is the answer to this problem? O3. That's a section of this O3 bundle. It gives us this surface S. So this is space all lines in P3, and you want the constraint is that the line should be contained in S. Okay? So the section and the cubic surface is given by a section of this O3 bundle. O3 is nothing but homogeneous degree 3 polynomials. Okay? And then you pull back to PU and project it down to by pi, and then take the Euler class. Okay? The Euler class is just a zero-dimensional cohomology class, and just Riemann-Roch calculation gives us this 27. Okay, but it's not the standard solution you find in an algebraic geometry textbook. The standard solution is this. First of all, you find that S is almost the same, deformation equivalent, to blow up of P2F6 points, and then you count 27. How do you find this? If you choose 2 points out of 6 points, you get a line. Okay, that's 6. Choose 2. If you choose 5 points out of 6, you get a conic, and it turns out that after these blow up, it just gives us these 6 conics give us line, and then there are 6 exceptional divisors there. Then you get 27. Anyway, it's already this is not so easy, right? But anyway, this is something you learn. I mean, this is something that every first course algebraic geometry, first course on algebraic geometry deals with. Okay, so. Okay.
Where is the cubic polynomial? This cubic condition is hidden inside.
Cubic polynomial.
Yeah.
Hidden inside.
I mean, where do you use that condition?
Is this O3? O3.
But what about the bottom?
Bottom is fact. S is somehow continuously.
So 6 points is the important part.
Yes. Row of 6 points. Yeah. Right. Right. So let's lift up the dimension by 1. So now we think about 4-dimensional space.
What about increasing the degree? Cubic instead of cubic, what about?
Yeah, we can do that. Yes. I'm just giving some rough some examples. And you can always ask. Yeah, of course you can ask for degree 4 case, degree 5 case. If you think about quintic polynomial, then you have to give more constraint, because the moduli space is continuous. Then you don't. I mean, so you need more constraint. Then you can talk about the number of lines and things like that. Right. Yes. Of course, you can also ask for a number of conics, number of cubics. I mean, there are infinitely many enumerative problems.
For T case, there is no line. General case.
Yeah. Right. So you can ask many questions, millions of questions in no code. And sometimes the questions are meaningless, sometimes questions are important, sometimes neither. Nothing. Okay, so let's think about higher dimensional case, P4 now, 4-dimensional space, and then you think about degree 5 polynomial, and think about 0 locus x. So now you ask the same question. How many lines are there? The answer is classical. It was found about 100 years ago, 2,875. How did they find it? Did they, I mean, it's not really easy to find this number by ordinary elementary methods and by deforming this to some nice case and like that. That's very difficult to do that. But if you do intersection theorem Grassmannian, GR25, first of all, think about all possible lines in P4, that's GR25, and do intersection theory for this condition, for this constraint. Then you get this. By Riemann-Roch calculation, you get this precise number, 2,875. So this is, I think, I mean, my understanding is that this is the reason why Schubert calculus was developed. Okay, to do that, to do this calculation, they had to know the cohomology ring of the Grassmannian. Okay, next question. So this is the case when degree line, we want count, this is counting of lines, this is the degree 1 curves, right? Then you can ask the same question. How about how many curves of degree D are contained in this quintic hypersurface, quintic threefold? Okay. Surprisingly, this is also a very difficult problem. And this is known for only for degree D less than or equal to 9. This is done by Gromfit invariants. And also there are precise predictions from mirror symmetry, whatever that is. Yes. Gromfit invariants are all calculated for all possible D, but what we do not know is that this condition gives us finite number of points or not. This constraint should give us finite number of points. Then you can say the Gromfit invariant gives us really the counting of degree D curves. But it's not known yet for D greater than 9. Okay, so I wanted to give you some flavor of these problems. The problems are quite easy to pose, but answers are often very difficult. Anyway, right now I want to give a 5-minute introduction to intersection theory in the moduli spaces. Okay, so what are they? So the most important thing is the philosophy is invariance under deformation. That's the key point for everything. So if you have two subvarieties of Z1, Z2 of a projective variety X, and we say these two are rationally equivalent, we want to say that these two are the Z1 can be deformed to the Z2 in a nice fashion, and the definition is this. If you have a chain of P1s, chain of lines, that's C, and then you want to have a variety W over C, and 2 points P1 and P2 in C, such that the inverse image of P1 is Z1, inverse image of P2 is Z2. So it's like you have a family of subvarieties, and at one point you have Z1, and at the other point you have Z2, and they are, well, continuously deformed. Z1 is continuously deformed to Z2. The punchline, the key point is that if two varieties Z1 and Z2 are rationally equivalent, then intersection numbers are the same. For any variety Y, intersection number of Y with Z1 is the same as intersection number of Y with Z2. That's the key point. So we get the notion of child homology, something called child homology, and that's given by this definition. You think about all possible closed subvarieties of dimension K in X, and then free abelian group generated by this set, and then take the equivalence classes by this rational equivalence. And then you take the direct sum of all possible AKs, and that's a lower star of X.
So the operation is what? The operation
group operation. The addition is given by this free-abelian group structure.
Oh, free-abelian.
Yes. And there is also multiplication, but for when X is smooth. But anyway,
Multiplication
is really given by intersecting two subsets. So there is some complication. I mean, if the intersection is transverse, then it's okay. But when it's not transverse, then you have to do some work. It's not so obvious. The multiplication structure is not so obvious anyway. Example. So projective space case is very simple. It's like the ordinary cohomology or ordinary homology. It's just Z, ZH, ZH squared, ZHN. HR is what? Intersection of all hyperplanes. Okay? So H is codimension 1, H squared codimension 2, HN codimension n, meaning that HN is a point. So now I can prove Bezout's theorem well, this very easily. So if you have degree D hypersurface in Pn, and this degree D hypersurface degree D hypersurface has child homology class D times H hyperplane, because you can continuously deform your any degree D hypersurface into the union of D hyperplanes. That's easy. You can do that by elementary, just writing down the equations. It's very elementary. Therefore, the intersection of C1, C2, Cn, n hypersurfaces is the same thing as intersection of D1H, D2H, Dnh. Then just it's the product of di's, and Hn is just point. So that's the proof. That's the proof of Bezout's theorem. Right? So only thing that I didn't prove is this theorem, this assumption. Let's just take it as true. Then you have this Bezout's theorem, very simple proof. Okay, so that's the basic idea of intersection theory. So everything just takes place in child homology group. Okay, so we take the push for, and then this child homology has punctorial properties. If you have proper morphism, then you can think about the image. If you have a subvariety of X, you can take the image, so that gives us push forward math. If you have a subvariety of Y, then you can take the inverse image, that gives us pullback. And also, very important thing is the Gisin map. If you have a regular embedding of X into Y of codimension D, then if you have anything in any subvariety of Y, then you can intersect the subvariety with X. Then the dimension drops by D, and then you get a subvariety of X. So that's Gisin map, which is in some sense the key point in the whole intersection theory.
When you define child homology, what is the differential operator and boundary operator, co-boundary?
There's no boundary operator, no co-boundary operator, just that, just the definition.
Don't you think?
Just
no co-homology.
no cohomology, just equivalence relation. Yes, yes.
So why do you call it
No complex here.
Why do you call it homology?
It behaves very much like, it looks very much like homology, as you can see in projective space. And there is natural math from child homology to ordinary homology. Okay, so that's intersection theory. In moduli spaces, what are moduli spaces? Okay, so for moduli spaces, as I explained the definition, but the sophistication or sophisticated issue about moduli spaces is the compactification problem. Because the moduli spaces are often not compact, but we need compactification, as we saw, in order to get nice intersection numbers. So, unfortunately, the intersection numbers depend on the choice of compactification. If you choose different compactification, you get different intersection number. That's the complication. Example. Think about all possible conics to tangent 5 given conics. If you have 5 given conics in plane, and if you want a conic which are tangent to all of these 5. Historically, about 150 years ago, about some mathematician gave an answer. The answer is 7776. Okay, his logic is this. If you think about all possible conics in P2, that's P5. Then he thought about the one condition, that's tangent to one given conic. That gives us a hypersurface of degree 6. Fine. So the set of conics tangent to 5 given conics should be an intersection of 5 hypersurfaces of degree 6. Now he applied Bezout's theorem, so the answer must be 6 2/5. What's wrong with this solution? It took a while to figure out that this is a wrong answer. It's a wrong answer because because if you think about, I mean, the space of smooth conics is not compact, and if you think about P5 as compactification, then you are in trouble, because the five hypersurfaces of degree 6 do not intersect transversely. In fact, they all contain the P2 in the boundary. So in fact, the intersection number is infinite, actually. So the correct answer was given by Chazels in 1864. The correct answer is 3,264. So he found that the correct compactification is the blow-up of P5 along P2, which is this bad locus. And this blow-up is something called the variety of complete conics, which is historically very important. And then he did intersection number. He found intersection numbers on this in this new compactification. And after this blow-up, there's all these 6 hypersurfaces intersect transversely now, and then you can really count the number of intersection points. And that number is exactly 3,264. So the very sophisticated issue here, you have to be very careful about compactifications. Okay? So if the moduli space of desired object is compact and the intersection of the varieties given by constraints is transverse, then just intersection numbers are enumerative invariants. But otherwise, you have to compactify and you calculate intersection numbers, and then you have to make sure that intersection numbers are the real intersection numbers. Okay, so there's some complicated issue here. Okay, so let me explain what blow-up is. Blow-up of Cn at one point is this Cn times is a subset of Cn times Pn minus 1. Is a pair of, okay, so an element here is a pair of V in Cn and Xi in Pn minus 1. As I said, Xi is a set of lines in Cn passing through the origin. So the condition is V is containing the line. Okay, so let's blow up. And you can think about the same thing. You can think about blow up along a smooth submanifold because locally a smooth submanifold looks, I mean, a neighborhood of smooth submanifold looks like Y times Cn, and then you can blow up the Cn part, and that's a blow up. Okay, so I just explained the words blow up as before. Okay, so let me talk about some recent issues of compactification of curved spaces. Okay, so that I worked on recently. So think about this space of smooth curves of degree d genus 0 in projective space. Okay, like in the conic case, degree line conics and cubic curves like that. And well, it's very easy to track that there's a smooth non-compact variety of dimension like this, and then and why is it so? Why is this a smooth non-compact variety? Because a smooth curve of degree d genus 0 in projective space is given by a map from P1 to PR. Genus 0 means that the domain is P1, so P1 to PR. That's given by an R+1 tuple of degree d polynomials, F0, F1, Fr, in 2 variables. So if you fix the basis of the space of all degree d homogeneous polynomials, then the map is, the smooth curve is determined by a matrix of coefficients. And if this matrix has maximal rank, you get a smooth curve, genus 0. And so you can say that, well, you can see that this space is a smooth, well, quotient of a smooth manifold by free group action. So that's how we can see that this is a non-compact smooth variety of this expected dimension. So for this case, you have many compactifications, right? So as I said, compactification issue is very important for enumerative geometry. The first compactification is given by some geometric invariance theory of Mumford's. So Mumford gave us a construction of taking quotients by reductive group when you have a projective variety in this. So this is a space of R+1 tuples of degree 3 homogeneous polynomials, and then you take the quotient by the action of PGL2, which removes the dependency on the choice of coordinates of C2. Okay, this is one compactification, and another compactification is Konsevich's moduli space of stable maps. A stable map to projective space is a morphism from a connected tree, a tree of spheres, tree of two spheres, and it should be a holomorphic map, and the automorphism group is finite. Then this is called stable map. And Konsevich claimed, although he didn't prove, that there is a projective moduli space which parameterizes all possible isomorphism classes of stable maps of degree D. And and this is, of course, this gives us a compactification of the space of smooth rational curves. And then there are also classical constructions by Hilbert scheme and compactification by Hilbert scheme and Charles scheme. Hilbert scheme is a projective moduli space of closed subschemes in PR with Hilbert polynomial P. And closed subscheme, don't be scared about this word of schemes, closed subschemes like that. It's nothing but homogeneous ideas in polynomial ring. This construction was given by Grothendieck, not Hilbert anyway. So Hilbert polynomial gives us a compactification. Also, likewise, Charles scheme, there is something called a similar construction by Charles, and that gives us compactification. And then also there is compactification by moduli space of stable sheaves. Okay, whatever that is. Okay, so you can think about if you have a smooth curve, then the structure sheaf is a coherent sheaf, and that satisfying certain nice properties called stability, and then, well, there is a nice moduli space construction by Simpson. And this also gives us compactification. So if you want to compare enumerative invariants, you have to compare these compactifications. And then recently I did the comparison. When D equals 1, everything is a Grassmannian. When D is equal to 2, these compactifications, this Mumford compactification, Konsevich compactification, Hilbert, Simpson, these compactifications are related by explicit blow-ups. Even in this simple case, in the conic case, it was not known how these compactifications are related. When D is equal to 3, it's a lot more complicated. So the GIT compactification, the Mumford compactification is related to Konsevich compactification by 3 blow-ups, 2 blow-downs, and the Konsevich compactification is related to Simpson compactification by 3 blow-ups, 3 blow-downs, and Hilbert compactification is just 1 blow-up from S. I'm sorry, this is just a little technical. Anyway, so I'm trying to show you the problem's not so easy. I mean, the moduli compactification issue is very often very complicated and not so easy. It's very difficult, even in this low degree case. Okay, so now, so I talked about moduli spaces. Now you can think about the invariance by applying intersection theory on this moduli spaces. Okay, so there are several such invariants called curve counting invariants. So it's just so the point is to count the number of curves contained in a given projective variety. So the first one is something called Grove-Witten invariant. It's nothing but intersection numbers on the moduli space of stable maps that I just introduced before. It's just different compactification of the space of smooth curves. Donaldson-Thomas invariant is the intersection numbers on the Hilbert scheme. That's one thing. Or intersection numbers on the moduli of stable sheaves. And also recent invariant by Pandey-Thomas that is about that they are this invariant is this intersection theorem moduli space of stable pairs, whatever that is. So anyway, the point is that the philosophy is the same, intersection theorem moduli space, but they just use different compactifications. And they are all different numbers. So in the definition of these invariants, there is some complicated issue, but you have to use virtual fundamental class in order to integrate cohomology classes. But let's not talk about this because I'm running out of time. So there's the issue of virtual fundamental class, and then there are some techniques for calculating these invariants. So far, the most calculated invariant is Gromov-Witten invariant. And the methods for calculating these invariants are the following. Just after so many papers, there are only 5 methods. First method is something called Witten digraph Verlinde formula. It's just associativity of quantum product. And second method is the most powerful method so far, localization by torus section. It's first introduced by Kontsevich, and that's the way he solved this problem that we mentioned before. In the degeneration technique, you degenerate your given variety into simpler variety and then just calculate Gromov-Witten there. And then there's a method by Grossman-de-Green-Loch formula by Gibbon telling his students. And a new technique, there's another technique by localization by holomorphic two-form. If your variety X has a holomorphic two-form, then you can localize your calculation to the locus where the holomorphic two-form degenerates. There's new technique, and well, this is one. I made small contribution in this method. And it's currently the most important, the most famous, the most hot issue in this area is the comparison problem. There are precise formulas comparing these invariants. Gromov-Witten, Darmstadt, Thomas, Van der Pont, these invariants are given. But nobody knows how to prove this. Nobody knows how to approach this problem at all. So I'm trying to work. I'm working on this because, and the reason why I wanted to compare these compactification is to get an insight about this comparison problem of these curve counting invariants. If you have an idea about this problem, please let me know. Okay, thank you very much.